And the engineering of the Raptor 3 is often summarized by its visual simplicity, a sleek, seemingly monolithic silhouette that belies the staggering complexity of its internal architecture. However, the most profound innovation isn't just what the engine is, but how it is realized. In the pursuit of the Star Factory cadence, SpaceX engineers had to solve a fundamental resource allocation problem: how to balance the extreme geometric requirements of a full-flow staged combustion cycle with the brutal economic necessity of mass production. And to a systems architect, this is the classic build versus buy or custom code versus standard library dilemma. If you write every single function from scratch in assembly language, you can achieve hyper-optimized performance, but you will never ship the product. If you rely solely on generic off-the-shelf libraries, your overhead will be too high and your performance will lag. The Raptor 3 is a masterclass in hybrid manufacturing, a strategic orchestration where 3D printing, or additive manufacturing, acts as the high-performance custom assembly, and casting or forging serves as the robust standard library. In the computational geometry of additive manufacturing in traditional manufacturing, you are limited by subtractive logic. You start with a block of material and remove what you don't need. This is inherently linear and constrained by the reach of a drill bit or the path of a lathe. Additive manufacturing (AM), specifically selective laser melting (SLM), flips this script. It allows for the creation of computational geometry shapes that are mathematically optimized for fluid dynamics and thermal management, but are physically impossible to machine. And within the Raptor 3, AM is the custom assembly code. It is reserved for the most computationally expensive parts of the engine: the injector plates, the pre-burner domes, and the intricate regenerative cooling channels that wrap around the throat and nozzle. These components are the inner loops of the engine's execution. They handle the highest temperatures and the most volatile pressures. And consider the injector head. In a legacy engine, this part might consist of hundreds of individual parts, manifolds, sprayers, and baffles all brazed or welded together. Each joint is a potential memory leak or a point of failure. In the Raptor 3, the injector is compiled as a single additive part. By using AM, SpaceX can design internal channels that follow nonlinear organic paths to ensure perfect mixing of the cryogenic liquid methane and liquid oxygen. This isn't just about making it smaller, it's about in-process optimization. The geometry is dictated by the physics of the flame front, not the limitations of a CNC machine. And for the computer scientist, this is analogous to loop unrolling, or SIMD, which stands for single instruction, multiple data, optimization. By printing these complex geometries as a single unit, you eliminate the overhead of fasteners and seals. This directly feeds into the engine's thrust-to-weight ratio. Every gram of metal that doesn't need to be a bolt or a flange is a gram that can be removed or repurposed for structural reinforcement where it actually matters. In casting, the O of one standard library, while 3D printing is the hero of the aerospace marketing world, it is a computationally expensive process. It is slow, the raw metal powders are incredibly expensive, and the build volume is limited. If SpaceX tried to 3D print the entire Raptor 3, the production rate would collapse. The Star Factory would become a star lab, stuck in a cycle of low-throughput perfection. And this is where casting and forging enter the pipeline. If AM is the custom assembly code, casting is the standard library, the O of one solution for bulk operations. Large structural components, such as the main combustion chamber jacket or the primary mounting interfaces, do not require the microscopic precision of an injector's internal veins. They require raw material density, structural integrity, and most importantly, speed. And casting allows SpaceX to produce the chassis of the engine at a fraction of the time and cost of printing. By using advanced superalloys, many developed in-house by the SpaceX metallurgy team, they can cast large-scale components that are good enough in terms of geometry, but superior in terms of throughput. And this is the resource optimization of manufacturing. You do not use a heavy, slow algorithm to solve a simple problem. A 3D printer takes hours to lay down a few millimeters of powder. A casting mold can be filled in seconds. By identifying which parts of the Raptor execution are structural, the boilerplate, and which are performance critical, the logic SpaceX ensures that the 3D printers are never the bottleneck for the entire factory. In the hybrid interface, where the code meets the library, the true genius of the Raptor number 3 lies in the interface layer, the points where 3D printed components are integrated with cast or forged parts. In software, an API, or application programming interface, allows a high-level language to call a low-level C++ library. In the Raptor number 3, the API is the robotic welding and friction stir welding that fuses these disparate manufacturing methods into a single, seamless unit. And this hybrid approach allows for variable fidelity. Engineers can place high-fidelity, 3D printed logic exactly where the thermal stresses are highest, such as the combustion zone, and wrap it in a low-fidelity cast wrapper, which serves as the structural housing. And this strategy is the primary driver behind the Raptor No. 3 legendary thrust-to-weight ratio. In Chapter 6.2, we discussed how the Raptor No. 3 achieved a TWR that dwarfs its predecessors. This wasn't achieved by a single breakthrough in physics, but by this manufacturing load balancing. Because the engineers can use AM to place metal exactly where the stress vectors dictate, and nowhere else they can strip away the dead weight of traditional safety margins. The engine becomes a physical manifestation of a lean executable. In metallurgy as the compiler. To make this hybrid approach work, SpaceX had to move beyond being just a rocket company and become a metallurgy company. In the world of software, the compiler translates your high-level intent into the specific machine code of the hardware. In the Star Factory, the metallurgical compiler ensures that the cast parts and the printed parts share the same data types. And one of the biggest challenges in hybrid manufacturing is the join problem. If you weld a 3D printed Inconel part to a cast stainless steel part, the difference in grain structure and thermal expansion coefficients can lead to runtime errors, cracks, or delamination under the extreme heat of a 10-minute burn. And SpaceX solved this by developing proprietary alloys like SX500, which are designed to be cross-platform compatible. These alloys are optimized to perform equally well whether they are being melted by a laser in a 3D printer or poured into a ceramic mold in a foundry. This ensures that the engine is a cohesive whole rather than a collection of parts. It is a statically linked engine where every component, regardless of its origin, behaves as part of a single, unified material system. And eliminating the spaghetti code of plumbing, the most visible result of this manufacturing philosophy is the deletion of the external plumbing. In Raptor 1, the engine was a spaghetti of sensors, wires, and secondary fluid lines. This was unoptimized code. Every external line was a manual patch added to solve a specific problem during the dev phase. And in Raptor 3, these lines have been refactored into the internal structure of the engine itself. Using additive manufacturing, SpaceX prints the fluid channels directly into the walls of the cast components. This is the equivalent of moving from an external API call over a slow network to an internal function call in local memory. And by integrating the plumbing into the hardware, SpaceX eliminates the need for thousands of individual fittings and leak checkpoints. This does not just make the engine more reliable, it makes it deployable. A Raptor 3 can be swapped out on the launch pad in a fraction of the time it took for a Raptor 1 because there are fewer dependencies to reconnect. The engine is a containerized unit of thrust. And the computational geometry of the nozzle of the Raptor 3 is perhaps the best example of this choose the right tool philosophy. The upper section of the nozzle, near the throat, experiences the highest heat flux and requires complex regenerative cooling channels. This section is a prime candidate for additive manufacturing. The geometry is tight and the tolerances are unforgiving. And however, as the nozzle expands, the heat flux drops and the surface area grows exponentially. 3D printing the entire nozzle bell would be a memory leak of resources. It would take weeks to print and cost a fortune. Instead, SpaceX uses more traditional fabrication methods, like roll forming and robotic welding of sheet metal for the lower nozzle. And this is algorithmic efficiency. You use the expensive, high-precision O of log n tool for the complex part of the problem, and the cheap, high-speed O of 1 tool for the bulk of the work. The result is a nozzle that is perfectly optimized for both performance and production. And deterministic manufacturing, the end of the golden unit. In the artisanal era of aerospace, companies would often talk about the golden unit, the one engine that happened to come off the line with perfect clearances and superior performance. This is a sign of a non-deterministic process. It means the manufacturing compiler has too many variables. And the Raptor 3 hybrid manufacturing approach aims for deterministic output. By using robotic casting and laser-driven 3D printing, the variance between engine number 200 and engine number 500 is reduced to near zero. Every engine is a bit-for-bit copy of the master design. And this determinism is what allows SpaceX to push the Raptor 3 to its absolute limits. If you know with 99.99% certainty the thickness of the cooling jacket at every single point, you can reduce your safety factors. You don't need to add buffer to account for human error in a weld. You can run the engine hotter and leaner, squeezing every last kilonewton of thrust out of the propellant. And the economic moat, throughput as a feature ultimately. The choice between casting and 3D printing isn't just about making a better engine, it's about making a more available engine. In the computer science world, the most powerful algorithm is useless if it cannot scale to meet user demand. And by mastering the hybrid manufacturing pipeline, SpaceX has created an economic moat that is nearly impossible for legacy competitors to cross. Most aerospace firms are either stuck in the artisanal past, casting everything with low precision, or are over-tilting into additive-only startups, printing everything with low throughput. And SpaceX has found the optimal runtime. They use 3D printing to solve the hard problems of fluid dynamics and heat transfer, while using casting and forging to solve the scale problem of mass production. The Raptor 3 is the first engine to treat manufacturing method as a primary design variable, right alongside chamber pressure and ISP. And this strategic balance ensures that the Star Factory remains a high-throughput pipeline, capable of churning out the executable thrust needed to colonize Mars. As we move from the external build of the engine to its internal logic, we see that this same philosophy of simplified complexity extends to the very heart of the engine's hardware, the elimination of failure points through total system integration. And the synergy between additive precision and casting's raw throughput is the hidden engine behind the Raptor 3 success. It allows for design that is simultaneously more complex in its internal logic and more simple in its external form. This reduction of external complexity is not merely aesthetic. It is a rigorous engineering discipline aimed at removing the legacy code of rocketry. By baking the complexity into the core components, SpaceX has paved the way for the next stage of the evolution, the total removal of the spaghetti that once defined the rocket engine. And 8.3, eliminating failure points, the philosophy of integration.